Information. This is the fourth day of the conference DSFD. Today we will start with the plenary talk with the speaker Matteo Lulli. Then we will split as usual in two parallel sessions. That will be the technical session 10 about the advanced methods in room Leone, so here in this web ID. Then in room Palma at the same time, the technical session 11 about the complex flows as a topic. Okay, so it's a pleasure to introduce my friend Matteo Lulli from the university. Let me take exactly the, okay. Southern University of Science and Technology of Shenzhen. Matteo Lulli deal with different topics, essentially computational physics, fluid dynamics, but also statistical mechanics and soft glassy materials. And the title of the presentation of today is a mesoscopic perspective on the Tolman length. Thanks to Matteo. You can start, please.
Thank you. Thank you very much for the introduction. I wish to thank the organizers of the DSFD for this opportunity to present our work, and especially to keep up the organization, to take care of the very different time zones we all come from these days. And it's important, it's very useful to keep the community connected in this time. So I share the screen. And please confirm that you see well. Okay.
Yes.
Very good. So I will talk to you today about this new mesoscale perspective on the Tolman length. Now, I will go in detail in a second. This work has been done in collaboration with Xiaowen Shen, Luca Biferale, Mauro Sbragalli, and Giacomo Ferrucci. So the point is that we wish to study the curvature dependence of the surface tension. This is not such a well-known subject on its own. And I can briefly say that such corrections are of paramount, of great importance for classical nucleation theory, and are expected to be extremely important in modeling gravitational inception. These are all problems where the curvature of interfaces at the beginning, for example, the nucleation is extremely large. So any curvature correction to the surface tension is going to play evidently an important role. We will focus mainly on multi-phase systems, although it is possible, it's been done to extend all these considerations to multi-component. So the curvature dependence lives in the thickness of the interface among phases. So this already is telling us that thinking about the surface as a jump is not good enough. And so a stepwise interface is useful, but it's an approximate model and it's a mechanical model of the interface. So we have, for example, now on the left, a flat interface, on the right, a curved interface. And starting from the flat interface, we can mechanically understand it by imagining a surface of tension, which is at the interface, separating the two phases, gas phase above, liquid phase below. By general arguments, by the argument of mechanical balance, the pressure on both sides must be the same, because otherwise the interface would be moving. And the surface tension is imagined as acting at the surface of tension, which in this moment is just sharp. On the right, there is a curved surface. In this case, there must be a pressure jump between inside and outside. And again, there is a surface tension, just sigma, the flat case is sigma naught, that acts at the surface of tension called Rs. Now, what we're going to see is that in general, sigma is different from sigma naught. The question is the details about this point. So let's begin analyzing the flat interface case with a thought experiment. I am basically following the presentation of the subject in the Rawlinson-Widom book, Molecular Theory of Capillarity, which is an extremely good book for the subject. And so the idea is to analyze the flat interface in a little more complicated setting, which is this one on the sketch. Let's begin from above. This is basically a box with 3 pistons. 2 of them are completely interfacing with either of the 2 faces. And the force exerted on each of these pistons is basically going to be equal to P naught times the area of each of the pistons. Whereas the force exerted on the bigger piston that is connected to 2 separated strings is not going to, I mean, the sum of the 2 forces, F1 and F2 of the 2 springs, is going to be less than P naught times the area. Why? Because the interface between the 2 faces is touching here. Of course, we need to imagine that this line also goes along the piston. And since there is tension there, it subtracts somehow. This is a very intuitive way of thinking about it. Now, and this is because of the surface tension. Now, this setting is good enough for us to allow for measuring the normal component, the tangential component of the pressure tensor. But what we're really interested in is to show clearly that the position of the surface of tension doesn't play any thermodynamic role. So we can understand this very quickly, intuitively, by performing a reversible compression. So by sliding a little bit the bigger piston to the left, and then we can tilt it. So we can tilt it one way or the other, in such a way that dV and dA are going to be exactly the same. So as a matter of fact, the surface of tension is going to be going up or down according to the tilt. But the amount of work that is done in this infinitesimal reversible transformation is exactly the same. So this is a very intuitive way to understand that the surface of tension on the flat case doesn't play a major role. Of course, it's important in our description to know where the separation between phases is, no matter what. But in this sense, Gibbs laid the basis of all these interface thermodynamics, and he proposed the concept of dividing surface. Gibbs dividing surface is any surface whose normal is parallel to the direction of the largest gradient. Now, as we have seen, the thermodynamics is independent on this arbitrary position because it doesn't even depend on the physical one in a sense. One feature is that for the flat case, the area of the dividing surface is invariant no matter where you put it. So according to the symmetries of the system, but so you just make a reasonable choice in a sense. And but the presence of an interface, since the interface is not sharp, are already visible in very basic quantities. For example, we can understand it very quickly from the total mass. The total mass will be, we can think about it as having a sharp interface. So the contribution will be the mass of the gas phase, the mass of the liquid phase, but then there will also be a surface there, which is this ms. A little more refined, this argument can be thought for the density. So we define the density jump, which basically takes either of the 2 values, the liquid density or the gas density, according to whether Z is above or below this threshold Z bar. And then we can define the absorbance, which is this integral. And this integral is measuring somehow a distance between the real interface and Z, which is not a stepwise function, and an idealized stepwise function. So, of course, since it is an integral, we can always find the value of Z bar such that this integral is 0. And this value corresponds to the equimolar surface. But this doesn't mean that the equimolar surface is the point of the interface. It's one of the possible choices. Another possible choice is the surface of tension. And the surface of tension is defined for the flat interface as the first moment of the surface tension. So that's how it's written. It's basically, if there was no Z and no normalization, this would be exactly the surface tension. So one multiplies by Z and normalized by the surface tension. So that's why one says it's the first moment. Now let's look at the curve case. Again, as we said before, there must be a pressure difference between inside and outside. And this happens simply because there is a tension. So the inside face is going to be squeezed, but at the same time, the system must be in equilibrium. So there is a pressure difference to compensate for the stress at the boundary. And differently from the flat case, the area of the Dioding surface depends on R. This is pretty evident. If we look at the vanishing of the compression work for movement of the interface, we get basically the requirement delta P dV minus sigma dA, which lead us immediately to the well-known Laplace law that many people in the lattice Goldstone community know very well. So let's look a little further in detail about what is the role of the arbitrary Dioding surface. Again, since it's arbitrary and we denote it by R, the arbitrary Dioding surface can be either fully inside the droplet, either fully outside. But we know that there must be no consequence on the physics of the system. So F needs to be independent or stationary, in a sense, on notional changes. That's how they are defined. And these notional changes are always indicated with square brackets in the literature. So if one does the calculation, the variation of the volume of the gas and liquids will be same in magnitude and opposite in sign. Then we will get the variation of the area and then the notional variation of the surface tension. So we get to something that is called generalized Laplace law. Very good. This generalized Laplace law looks exactly like the usual one, plus the derivative, the notional derivative of the surface tension. One point that it's good to have in mind is that the delta pressure is an observable, so it cannot depend on such on the position of an arbitrary Dioding surface. At the same time, this generalized Laplace law gives us a way to define the surface of tension, which is the position at which the notional derivative, d sigma in dr, vanishes. At this position, we recover again the Laplace law in the same form. And that's why the Laplace law is always understood as acting on the surface of tension. Yes, valid as the surface on the surface of tension. So we can also define again the equimolar surface with a similar requirement as before, the vanishing of the adsorption. In this case, we can make it look a little bit simpler. So basically, the requirement is that the total mass is equal to the mass in the inside face plus the density of the outside face multiplied by the complementary volume. If one resolves this, one gets this formula, which is very useful. Actually, it gives a nice estimate of the size of the droplet. It can be used. It's actually frequently used in LBM because it just requires global quantities. You don't need exactly to know where the droplet is. You just need to know that there is one droplet. And however, the Laplace law with this radius is not the one that you're expecting, because there is the first term and the derivative. Now, so this Laplace law is not exactly measuring the surface of tension in this sense, but there are corrections. The surface tension, sorry. So let's go to the Tolman length. Now that we know that there are different concepts of dividing surfaces with different roles, physical roles, and so on, we can understand begin to understand the idea of Tolman that he proposed in now in 1949, quite some time ago, that given that the surface of tension and the equimolar surface of the flat interface differ, this implies a dependence on the curvature of the surface tension. Of course, this curvature dependent surface tension is expected to gain back the flat interface value in the zero curvature limit or in the infinite radius limit. And Tolman proposed a curvature expansion, like a power series expansion of the surface tension. And at the first order, the zeroth order is simply the flat surface value. The first order is given by the Tolman length. The coefficient is given by the Tolman length twice. So is there a way to estimate the Tolman length? Yes. Given the generalized surface tension, what we know is that this is the generalized surface tension. We need to be at the minimum to be at the surface of tension. And so we can just follow the minima of all the generalized surface tension and extrapolate their behavior near the zero curvature limit. So how to do this? We can still use a Laplace test. It's just that we need to know the delta pressure, the radius of the surface of tension, and the flat interface surface tension. So the point that we're going to face in a second is how to measure this surface of tension, Rs. But so basically the main point, the main takeaway here is that given this generalized surface tension, the physics is at the minimum, is at its minimum. That's all that matters. The rest is more a parameterization issue, but the minimum contains physical information that can be extracted in the zero curvature limit. Okay, that's one. So now we can go back again to the physical importance of the Tolman length. So let's pick up again the classical nucleation theory. Nucleation rates depend exponentially on the value of the surface tension. This makes delta extremely important because the value of the surface tension is at an exponential, as the exponent of an exponential. So any tiny difference is going to count. And in fact, we can see it from here. So this is, for example, the nucleation rate. J naught is actually a pretty non-trivial constant. And this is the free energy, the free energy barrier for nucleation. Typically, in classical nucleation theory, there is the so-called capillary approximation that stops at sigma naught, so only for the flat value of the surface tension. Whereas it has been proved in a few theoretical works that also recent ones, that this correction actually can be extremely important in some cases, where even the classical nucleation theory gives out some paradoxical results. So it's pretty evident that whenever the interface is small, considering corrections begins to be extremely important, begins to be very important. There are many years of studies with many molecular dynamics studies. Now I'm citing just a few Monte Carlo simulation studies and density fractional theory modeling. The literature is very diverse. There are more than 70 years of literature. So many different authors have contributed. And there are some delicate points. But what we can tell for sure is that molecular dynamics and Monte Carlo are acting on microscopic scales. Whereas density functional theory provides more of a continuous description. So there is a mesoscale gap to be filled. So the lattice-Boltzmann can bridge this gap and bring in hydrodynamics because none of these approaches apart from explicitly bringing the hydrodynamics in a mesoscale way. And moreover, lattice-Boltzmann would be far computationally more efficient than molecular dynamics and Monte Carlo. So that's why we took the challenge. So let's see how we proceeded. Actually, we basically used the simplest implementation of the Shanchen multi-phase model. And I'm reporting here very quickly the details. We use this lattice-Boltzmann equation with a forcing term. The collisional term is the single relaxation time GK. Then we use the Guo forcing, and the equilibrium is, as usual, the Taylor expansion to second order in the velocities, and the equilibrium velocity is shifted in this way. We're using the D3Q19, and which is depicted here. So let's move on for the forcing itself. The forcing is responsible for the phase separation, and this is the Shanchen forcing that lives on the lattice and is built on top of this pseudo potential function that is a local function of the density. So the force itself is built up as a sum of products of these pseudo potentials, and we report here for clarity the value of the weights. The stencil is basically the same apart from the zero velocity because it's not needed here since we are proportional to the stencil itself, to the vectors. And this force gives rise to a bulk pressure. The bulk pressure can be written in this way, where E2 is equal to 1. And this equation of state, because it's a pressure as a function of the density, allows for phase coexistence when the coupling G is below a given critical threshold. What does it mean? It means that it is possible to have the same value of the pressure in the bulk for two different values of the density, say the gas and the liquid one, and they're equal to 0. But of course, once there is not just one combination of these three values, P0, G, and N, and L, you need another constraint, which is given by this integral equation. And this integral equation, where epsilon in this case is equal to 0, this integral equation is in a sense the analog of the van der Waals construction, of the Maxwell construction, in the van der Waals case. Okay, so once we have this, we can have phase separation as is depicted in the sketch here. So in this case, for example, we have a droplet. Now, the next step is how to determine the surface of tension, the generalized surface tension, so that we can determine the position of the surface of tension at its minimum, and then move on in the evaluation of the Thomann length. To do that, we need the lattice pressure tensor that was developed in 2008 by Zhao and Shen. And the important feature of this lattice pressure tensor is that, for example, the normal component of flat interface is constant to machine precision. So the mechanical equilibrium condition is completely realized on lattice, clearly not in the continuum. And which is a big, this property allows for very precise estimations of the bulk properties of equilibrium. And we can use actually this lattice pressure tensor to compute the generalized surface tension. Just to be a little more precise, we can clearly see that the lattice pressure tensor divides in the kinetic or ideal part and the interaction part on the right. Starting from the mechanical equilibrium condition, which is that the forces inside are 0, which is basically equals to the divergence of the pressure tensor. We can derive this integral definition for the surface, the generalized surface tension. And again, we needed to define the jump function for the pressure, which looks exactly the same as that of the density, and the tangential part of and this is the tangential part of the pressure tensor. In our case, we choose the radial axis to coincide with the x-axis, and the tangential part will correspond to either PYY or PZZ. Okay. Whereas the normal one will be Pxx. I didn't write it. So these are the simulation details. We consider droplets and bubbles. The size ratio with respect to the system is that the radius is always equal to L4. The range of system sizes goes from 41 to 355. We consider two different pseudopotentials, exponential minus 1 over n and 1 minus exponential minus n, which are common choices. And we do this because we want to see the result in generality, in a sense. And then we consider the range of G. And I give it in a normalized notation, reduced coupling in a sense. And we will see why in a moment. And these values are such that spurious effects are minimized. Very good. Let's begin from the flat interface surface tension. We can see that the flat interface surface tension is defined as the integral of the normal component minus the tangential one that can be approximated in these terms of the pseudopotential. But interestingly, if we plot the data against the reduced coupling, data collapse. Data collapse very nicely. It was already known, and data collapse in a power law fashion according to mean field exponents. It was already known that the exponents are mean field for the Shanchen model, but at the same time that the prefactor of functions changing the pseudopotential is the same is a bit of a novelty. And what this means for us is that, practically speaking, is that we can use only one scale to represent all the data independently on the pseudopotential that we're using. Very good. So now we can move on to the generalized surface tension. Again, this is the generalized Laplace law. What we know is that we can actually integrate this equation in a dimensional form, as it is reported here. And what is interesting is that this integral doesn't depend on anything. It doesn't depend on the size, on the temperature, whether it's a bubble or a droplet, and so on. But this is pretty clear to understand because this is a notional dependence. However, it's a good check. So we plug into this formula our tangential component of the lattice pressure tensor. We do the calculation, and we see that this quantity actually fulfills this requirement. So if in the plot on the right, basically there are all the data coming from different pseudopotential, different bubbles, different droplets, different values of the coupling constants, and so on, and they all collapse. So even though this is not a physical information on its own, this is telling us that we are manipulating the quantities in the right way. And we can extract from the minimum the value of the surface of tension. Now, let's look at the Young-Laplace law, which is plotting the pressure jump against the surface of tension. And as we can see, there are clearly corrections. So the straight lines are what you would have expected if the surface tension wouldn't depend on the curvature. But as we can see, the data are diverging. And for the red color, we are near the critical point. We go further away from the critical point, going towards the blue. Moreover, the droplets corrections are opposite with respect to the bubbles corrections. And if we plotted, as we all know, because many times this test has been run, if we plotted this data with respect to the equimolar surface, the corrections would be much smaller, almost unnoticeable. How to measure the correction now? We do exactly what we said before. We plot the pressure jump times the surface of tension, normalizing by 2 to the value of the flat interface surface tension. And we expecting to get minus this function to which is linear in the curvature. And indeed, we get very nice linear dependence in the curvature according to the temperature. And what we see is that the closer to the critical point, the steeper the slope. And the data allow us to fit linearly near the zero curvature limit very nicely. So as a matter of fact, that's the news. The Shan-Chen lattice-Boltzmann model captures the Tolman length. To see this Tolman length, all that we needed to do, which is in a sense non-trivial, was to place the surface of tension, to compute the surface of tension, and look through the lens of the surface of tension at the system, not through the lens of the equimolar surface. So now let's look more in detail at the temperature dependence of the Tolman length. And as we can see, there is another power law. The exponent is -1. It is compatible with the mean field values of beta and nu according to this relation that is being computed in 1992, that this exponent should be -nu minus beta. And again, all the data are still collapsing no matter the pseudo potential that we're using. We can double check with another definition that is known in the literature to be not exactly identical, but still compatible in our expectation. And this is basically given by the difference between the equimolar radius and the surface of tension radius. And as we can see, we need to look at the zero curvature limit, which is represented here by these black diamonds. And the Tolman length, of course, is growing again as the temperature reaches the critical point. Again, we have a reasonable power law. Again, the exponent is -1. The relative value seems to stabilize around the factor 2 between the previous definition and this one. But in the literature, it's known that these two definitions can differ. Okay, so very well. Let's look at the conclusions and the perspectives. The Shan-Chen lattice-Boltzmann model for multiphase captures the Tolman length. It is positive. It shows power law scaling near the critical point. The data display universality with mean field exponents, and the value of the exponents is compatible with the analysis of previous works. So the Shan-Chen model looks like a promising way to bridge this mesoscopic gap that we've been talking about before in the study of the Tolman length. Future steps will be to assess the role of the Tolman length with non-trivial hydrodynamics, because of course, these are hydrostatic measurements, to formulate a strategy to tune the value of the Tolman length. And for this, we really need an accurate control of the lattice pressure tensor, of which we moved the first steps very recently. Not first steps, I mean, we worked on it recently. And we will extend to multi-component systems. So last announcement, we are hiring. So if anybody is interested in this subject as a postdoc, please let us know. We will be very happy to talk to you. Okay, so now the acknowledgements. So these are the fundings that have been supporting this work. Since I'm at 31 minutes, I would like to speak very briefly about another matter, which is the idea.deploy framework. Basically, all the results that I've been talking about can be reproduced locally by anyone. Basically, there is in this idea.deploy framework, there is full access to the code, to the scripts for creating the figures, and this is already true with the pressure tensor work that has been published. And the idea.deploy framework is bridges the low-level and the high-level usage for computational physics. It's based on the very good modules PyCUDA, PyOpenCL, NumPy, and so on. At low level, which is C, C++, it provides a meta language that can be used to automatically generate and compile CUDA and OpenCL codes starting from a single agnostic code. At mid-level Python, it provides parent classes that can be used to facilitate the coding, so for memory allocation, multiple streams, kernel invocation, IO management, and PI. And PI is on the works now. At high level, it can be accessed through Jupyter notebooks relatively easily, and so that anybody can reproduce all the content by simply pushing Shift-Enter a few times. But that's all that's needed at the highest level. And the goals and the features is that these structures should foster numerical reproducibility, which is a pillar of the scientific method. Contribution acknowledgement, because the code is growing modularly. It's not a monolithic code. It's not thought explicitly for lattice Boltzmann or anything else. It's a framework. And then there is the concept of numerical proximity, which is that in these frameworks, very different computational physics areas can overlap with the same API calls, with the same high-level usage. So the hope is that this common ground may lower the free energy barrier to the mutual interaction of different computational physics tools. And finally, so there are these two, you can go on the GitHub page. There are these two, one has been published, which is the structural isotopy that can be completely recreated. And then also the mesoscale perspective, which is under review now. You can go, take the code and have a look. Okay, so while I take the questions, I will try also to do something else, because I would like to show the notebook if I manage, but I think it's enough for now. Thank you very much for your attention. I really appreciate this chance again to organize it. Thank you. And
thank you too for your nice presentation. And there are already a question. Please say yes.
Please.
You can, yeah.
Thank you. Well, first of all, thank you very much for the very interesting talk. So I had a question about the Tolman length. So I guess the conclusion of your talk was that the Shanshan method and the mesoscopic formulation is able to capture the Tolman length and its temperature dependence. But if we think about it, so the Tolman length is a direct consequence that appears as a result also of the van der Waals capillary fluid theory, right? Or any other single component gradient fluid theory.
Yeah, if you want, yes.
Okay, so then you should also be able to get the effects of the Tolman length by solving the corresponding macroscopic equation, which would be in that case Navier-Stokes plus Korteweg.
It depends on the model you're using. There is a catch. Not all models can. Because what are you referring to, for example?
Look, for example, so the endpoint was, if we look at the Shanshan formulation and we do a macroscopic analysis, we can see that the momentum equations that you recover are nothing different from the Navier-Stokes equation plus a non-ideal equation of state, therefore a non-monotonic EOS, plus something that looks like the surface tension of Korteweg, which would be the surface tension of Korteweg if your effective mass was density itself. In this case, it's an exponential function that looks like density in the limit of vanishing density, right? So, which means that the two are equivalent in a sense.
They're very close. I mean, the problem is that if you use, so the biggest issue is that your theory needs to have an asymmetry. So for example, if you use a square gradient theory with a potential that is perfectly symmetric between the gas and the liquid phase, that thing is not going to have any Tolman length. That thing is going to have possibly higher order corrections in curvature, but not the first order one. So
yeah, when you say symmetry, is that symmetry in the equation of state itself or the discretization?
No, the symmetry, I mean, in the free energy. If the value of the free energy for you is the same in the liquid and the gas phase, no Tolman length. you must have an asymmetric theory. So that's what actually this is an interesting point, because the literature, we know that Shanchen is not the only multi-phase model for lattice Boltzmann. And in the literature, the models starting from free energy have contemplated the possibility, it's written in several papers, that they've contemplated the possibility of curvature correction, but back in the 90s, I mean, there are PhD theses and so on. They always discarded them because they were aware that since their theory was symmetric, there was none. So in this sense, what you say, if I get correctly the question, I mean, I forcibly agree with you in a sense, but the Shanchen model has a twist that allows for this asymmetry between phases. And
but just as the last part, if I may interrupt, so this symmetry in the context of the free energy formulations, you have it only in the cases where they consider the double whale potential, which is fully symmetric. But if you go with a realistic cubic equation of states, say van der Waals, you get the same asymmetry.
If you go cubic, I suppose so. Yes, yes. I didn't claim that this is the only theory.
Okay.
I claim that this is the first time that this is shown. That's of course. Mathematics is mathematics. There's no discussion.
Thank you.
Thank you for this interesting question and for the clarification. Thanks again to Matteo Lulli for the presentation.
Thank you very much.
Okay, now we can move on. From this moment, the conference is split into parallel sessions. I remember that here we will proceed with the technical session 10, the topic advanced method, while in the room Palma will start now the technical session 11 about the complex flows. So let me introduce the first speaker of the technical session 10, which is Dr. Wang. Now I will give him the opportunity to share the screen. Okay, you can try to share the screen.
Okay. Can you see my screen now?
Yes, yes.
Okay, that's fine.
And he's presenting a talk co-authored by Professor Kai Luo and Dr. Lilin Fei. The title is Study of a Realistic Droplet Impingement Dynamics using a Unified Lattice Boltzmann Method. Please, thank you.
Okay, thanks for your introduction. Hello, everyone. My name is Geng Wang, a PhD candidate in USL. I'm very glad to come here and introduce our recent work, which topic is study of realistic droplet impingement dynamics using a unified lattice Boltzmann model. Also, I appreciate a lot of the continuous help from the co-author, Professor Kai Luo and Dr. Fei in ETH. Droplet impingement is a very common multi-phase phenomenon in engineering, especially for the liquid droplet. There has already been observed a lot of interesting phenomena, such as the droplet pancake bouncing and the generation of rotating droplets. Some more complex dynamics can be observed when droplets impacting at high Weber number and Reynolds number, such as droplet crown splashing and the bioring droplet collision spray. Gaining a further physical understanding of droplet dynamics could benefit a wide range of applications. In the past decades, many multi-phase lattice Boltzmann models have been proposed. However, many drawbacks are still involved in the traditional multi-phase LB model, such as the thermodynamic inconstancy, large spherules velocity, and the low achievable density ratio. In recent years, various LB products have been proposed to overcome those drawbacks. The existing advances can be generally divided in two parts. The first part is constructing improved collision operators, such as the MRT schemes, castatic lattice Boltzmann or the entropic lattice Boltzmann. The first part is developing improved forcing terms. Nevertheless, the combination and the shift between the collision operators or forcing models still complex and could bring additional efforts in programming. And it still lacks study to clarify the relationship among different collision operators. Thus, it's desired to propose a unified model which can integrate various various developments in LBM collision operators and models. So recently, Law et al. Proposed a unified lattice Boltzmann model, which so-called the ULBM. It integrates widely used collision operators into a unified framework. The ULBM can either switch between different collision operators with a very simple modification, or easily extend the improved schemes for a specific collision operator to another. Benefited by its universality and flexibility, the ULBM could be potentially applied to multi-phase flow with an extensive range of realistic parameters. The key power of the flexibility in ULBM comes from three different metrics, which are the transformation matrix M here, and the shift matrix N, as well as the reaction matrix S. The transformation matrix is used to transfer the distribution function to raw moment. The shift matrix N is used to shift the raw moment into the central moments. By using these two different metrics, the model can be switched between the MRT and the castatic lattice Boltzmann. For example, if we directly use the central moment set, this model equals to the castatic lattice Boltzmann. If we set the shift matrix N as a unit matrix, this model can reduce to MRT. Regarding the reaction matrix S, for the moment-based collision operator, such as the CLBM, castatic lattice Boltzmann, we can further extend it to the KBC entropic lattice Boltzmann model by using the entropic stabilizer in reaction matrix S. For MRT model, we can reduce it to the LBGK if we set all elements in reaction matrix S as the same. Then I would like to introduce how to construct a ULBM for the realistic droplet dynamic simulation. The targets of this model, including simulate the large density ratio multi-phase flow, achieving low superior velocity, and able to keep the thermodynamic constancy and the adjustable surface tension. Here we choose a castatic ULBM as an example. The first step to construct the ULBM is to choose your collision operator. And here we choose a central moment-based collision operator. Then is select your moment set. In order to reduce the computational cost as well as keep the numerical accuracy, we choose a non-orthogonal moment set in this work. Thirdly, is to determine your forcing terms. And for example, here we use this central moment-based forcing terms. Then is to calculate the transformation matrix M and the shift matrix N. And the details for the calculation of these two metrics can refer to phase work in PRE 2018. Then the next step is to select your reaction matrix. Usually, the reaction matrix for the reaction parameters for the second order moments are related to the fluid viscosities, and all the other high order parameters can be chosen freely. Besides, we can also implement the entropic product for the high order reaction parameters to satisfy the maximum entropic theory, which also can significantly increase the model stability. Finally, is implement the additional terms. Here we implement the additional forcing terms proposed by Li et al. For these forcing terms can achieving the thermodynamic constancy and the tunable surface tension. Remarkably, in previous work, those additional terms are usually used in the MRT model, but thanks to the ULBM, it can be also adopted in the castatic lattice square model in this work. After the introduction of the numerical model, here I want to show some results achieved by using the ULBM. This slide shows the validation results for the KBC ULBM. As mentioned before, the KBC ULBM is achieved by implementing the entropic stabilizer into the high-order reduction parameters. Firstly, we validate the model by reproducing the pancake bouncing when impacting superhydrophobic parallel surface. 3 different cases are simulated. It can be found our simulation results are in excellent agreement with the experiment. Then a further qualitatively comparison is conducted by simulating a water droplet impacting a flat superhydrophobic surface with various Weber number. The Weber number is ranged from 6.4 to 120, and the 2 different quantitative parameters are comparison, which is the maximum spreading diameter and the dimensionless contact time. And the results are compared with the experiment data, previous simulation, and the theoretical prediction. Also, we can find our simulation results in line with the previous work. Finally, we reproduce a bioring droplet collision experiment. As shown in the figure, the excellent agreement of the experiment and our simulation can be found. The validations in this slide are conducted by using the non-orthogonal MRT ULBM. The non-orthogonal MRT ULBM is achieved by setting the shift matrix N as a unit matrix, and the transformation matrix M is achieved by the non-orthogonal moment set. Here, 2 cases are shown. The right one is a water droplet of central impacting a rigid superhydrophobic surface. 3 cases with different of central distances are simulated and compared with the experiment data. The left one is a droplet impacting a curved superhydrophobic surface. As we can find, the simulation results are both qualitatively and quantitatively agreed with the experimental results. By extensive validations, we can find our ULBM model can actually reproduce various droplet dynamics with different model choice. In fact, the ULBM has already been adopted to research various realistic droplet dynamics. Here, I would like to introduce a case for engineering applications, which using the non-orthogonal MRT ULBM to simulate a droplet impacting the superhydrophobic masonry. This work gave a comprehensive parametric study to investigate the dynamic process of droplet impacting, penetration, and fragmentation. The results in this work clarify the influence of the liquid property in droplet maximum spreading diameter, jet breakup length, and beyond. The qualitative data achieved by using the numerical approach benefits the understanding of this complex droplet dynamics. Another work is also conducted by using the non-orthogonal MRT ULBM. It simulates a water droplet penetrates microparallel array. 3 selected cases with various parallel geometries are shown in the red figure. In this work, we carry out a parametric study by changing the droplet impacting velocity, microparallel opening fraction, and the wettability of the microparallel surface. It's found that the change of the droplet impacting velocity and the configuration setup could can significantly influence the droplet penetration dynamics. The red figure shows the process of droplet pancake bouncing by impacting superhydrophobic surface, superhydrophobic pillow surface. The simulation is conducted by using the KBC ULBM, as it can be observed, owing to the capillary resistance. The spreading of the top part droplet is faster than the bottom part droplet. In contrast, the retraction of the bottom part droplet is easier than the top part droplet. Thus, it can be found that the top part droplet is still spreading or retraction when bottom part droplet is fully retracted and bounce off from the pillow surface. The numerical simulation gave a detailed insight into the reason for the droplet pancake bouncing. The cases here also can demonstrate the power of the ULBM in simulating various droplet dynamics when impacting with complex geometry. Then I would like to show the ability of our ULBM in simulating the droplet dynamics when with large impacting Weber number and Reynolds number. The first case is droplet crown splashing when impacting the thin liquid film. This case is achieved by using the non-orthogonal MRT ULBM. The impacting Weber number ranges from 250 to 550, and the Reynolds number is kept as 5,000. By comparing the simulation results in the right figure with the experiment results in left figure, it shows that our model can actually reproduce the dynamic process of crown and the satellite droplet formation. Also, like the experiment phenomenon, for the lower Weber cases, only the formation of the liquid crown is observed. For the higher Weber cases, both liquid crown and satellite droplets can be found. Besides, it shows that the dynamic process of crown formation is accelerated as the Weber number is increased. Finally, we test a higher demanding case by using the KVC ULBM. We reproduce the Byron droplet head-on collision spray at a very large Weber number and Reynolds number. In this simulation, the maximum Weber number can reach to 800, and the maximum Reynolds number can over 7,000. As shown in the figure, for the cases at a lower Weber number and Reynolds number, as shown in the red top figure, after the droplet collision, a liquid disk forms and expands. During the liquid disk expanding, some liquid rims tear off from the liquid disk and continues break up into many small satellite droplets. Then we increase the Weber number and the Reynolds number. As shown in the bottom right figure, we can find that the liquid disk spreading faster and the diameter of the flaked liquid rims are thinner. After the liquid rim break up, the generated satellite droplets occupied all the simulation domain rapidly. Qualitatively, those simulation results agree well with the previous experiment data. However, some difficulties still occurs in the present model when simulating the large Weber number and the Reynolds number multiphase flow, such as we are unable to capture the fingering separation, which is observed in the experiment. And we are still conducting study for this problem. In summary, in this presentation, we introduce a unified lattice Boltzmann model and show its accuracy in modeling realistic droplet dynamics by various validations. Then we demonstrated the power of this model in simulating various realistic droplet dynamics. Finally, we show its ability in simulating large Weber number and Reynolds number cases. The following conclusion can be drawn. The ULBM formulation has unified the different collision operators. And using ULBM, it's easy to switch between the models and select the optimized model for the chosen application. and extensive validation has been carried out in multi-phase flows. Finally, a KBC entropic lattice Boltzmann has been implemented into the ULBM to simulate the droplet splashing, and the Weber number is 800 and Reynolds number can over 7,000. So that's all my today's presentation, and thanks for your listening. I'm open for any question.
Thank you, Dr. Wang, for this nice presentation. Okay, we'll start to have some questions. Okay, the question is, if I understand correctly, your unified lattice Boltzmann method relies on linear transformation matrix to move from the population space to a given moment space, and vice versa. Yet this formalism cannot be used for cumulants, since the latter are computed through nonlinear transformation of central moments. How would you then extend your unified formalism for it to include the cumulant approach? Maybe using correction terms. I think the sense if the unified lattice Boltzmann method can be extended also to treat the cumulants.
Okay, I think it. In fact, currently we are we haven't extended it to some covalent approach. If you talking about the entropic product, because the entropic stabilizer in our works is calculated using the moment set. So if you means you are interested in how to calculate this entropic stabilizer, you can refer in our recent work.
Okay, thank you. I think there are no further questions, so we can move to the next speaker. Thanks again to Dr. Wang.
Thank you.
Okay, and so now we can move on to the next speaker. I give you the permission to share your screen. We will see if you are able to do it. Try, please. Yes, it is working. Great. Okay, let me introduce Dr. Zipunova from the Keldysh Institute of Applied Mathematics of the Russian Academy of Science, former Soviet Union Academy of Science. Please.
Hello, you can call me Lisa. My work with my colleagues is about construction of mass-conserving schemes for LBM with interpolation of the off-grid values. The weak point of LBM is the inability to describe high thermal flows. The point has been proposed in 2019 in the following article. And in this method, in each mesh node, the discrete distribution functions are represented as a series around the local gauge. The gauge is determined by the velocity and temperature. The transformation between gauges is performed by moment matching. The streaming is performed from off-lattice points and is supplemented with interpolation. The method is very promising, but it has some flaws. There is no mass and moment conservation, and the 3D simulation is not feasible due to high costs. In the particles on demand method, there are two phases in each time step: streaming and collision. Let's look at streaming step in more detail. It is much more difficult than in LBM, but collision is easier in particles on demand than in LBM. For each time step, for each mesh node, for each discrete distribution function, we stream it from the point corresponding to velocity, EI, and velocity and temperature for the gauge are taken from the next time layer. This is off mesh point, as you can see in picture. Discrete distribution functions in this point is interpolated using Lagrange interpolation. L is the size of the interpolation template. Interpolation stencil could be fixed to mesh node or unfixed and moving with the point from which we stream. For interpolation, we have to convert discrete distribution function into a new gauge for all template points. So we need to convert and multiply matrices a number of times, which causes a number of problems. So last year, we developed a RegPont method. For RegPont method, I want to look closely at gauges. Gauge is a couple of values, temperature and velocity. Standard gauge is 0 and 1. In it, we can calculate raw moments as shown on the slide, and also there are moments of Hermit. We call them D by it's D, and distribution function can be approximated using a Hermit expansion in a moving reference frame, which is associated with gauge. On these concepts, last year we proposed the RegPont method. In RegPont method, all data is stored in moments n in the standard gauge. For each mesh point at each time step, streaming starts with a prediction of a new gauge as a gauge from a previous time step. Using this gauge, we calculate the point from which we stream. Then at this point, we interpolate moments. Then with the help of moments, we calculate moments in moving frame. From D, we calculate discrete distribution functions using Hermit expansion and stream it into the point X. After streaming in this point all needed distribution functions, we can calculate new values of speed and temperature and correct our predicted gauge. Iterations proceed till we find the right values of speed and temperature, and once iterations stop, we can calculate collision and new values of moments in standard frame M. All this is very fine, but still no conservation laws, because interpolation don't provide conservation. So let's take a closer look at interpolation process, streaming, and following it calculation of moments. For simplicity, we'll consider streaming to origin of coordinates. By the definition of moments M, after streaming, we'll calculate moments on the next time layer using this sum. In the same time, used in this some discrete distribution functions will be interpolated using Lagrange interpolating polynomial. Our streaming point depends on discrete velocity, so interpolation coefficients are discrete velocity polynomials. So if we collect all used sums needed to calculate moments at next time layer, open the brackets and sum over all quadrature points, we'll have expression with which we could predict future values of moments using current values of higher order moments in nodes of interpolation stencil. So to predict future values of moments, we need to calculate and store higher order moments. If we can predict future values of moments, then we don't need iterations, because we don't need to guess future gauge. This was in work of Zakirov on in 2019. Let's carefully observe how it is done for one dimension and for 3-point fixed interpolation stencil. You can see that interpolation coefficients of Lagrange interpolation are second order velocity polynomials. So when we open the brackets and sum the results in expression over all quadrature points, we'll have second order moments. On last two lines, moments have superscripts and subscripts. Here and after, superscripts correspond to coordinate, and subscript correspond to order of the moment. So you can see such interpolation provides points symmetric flows, and such flows ensure conservativity. But when we try to do the same process for 3 dimensions, we have some problems. Firstly, the order of coefficients of Lagrange interpolation became much higher. Now, if we want to predict future temperature, we need to calculate and store 8 order moments, and this is only for such small stencil. Also, following equation can be reimagined as symmetric flows, and also on practice we applied this method on very simple problem and find that it's not conservative. So we came to conclusion that Lagrange interpolation in more than one dimension will not work conservatively. So we still can predict moments, but this process will not be conservative nevertheless. So we took a step back to reconsider the interpolation method. We agreed that we need the expression for future moments looks something like this. So it has symmetrical flows and the moments order is not so high. So all we need is to find expression for coefficients A, B, and so on. And to provide such expression for future moments, interpolation of discrete distribution function must look like this. To find coefficients, we have written out the Taylor series expansion for different stencil points and tried to combine them to provide second order approximation. Here and after, let's use simplified notations. So Taylor series for central point look like this. And for several neighboring points, it looked like this. Parts of a series that differ from series of central point highlighted in yellow. So we need to take a series for central point and add such combination of discrete distribution functions from neighboring points that only f will stay. Firstly, if we subtract value at -100 from value at 011, that only highlighted in yellow terms will stay. Next, if we sum these values and then subtract central point values, only highlighted in yellow with no minus plus sign will stay, and so on. Using such reasoning, we developed the interpolation expression for discrete distribution function and therefore expression for future moments. This expression is symmetric, provides second order approximation, and to predict future values of moments, we need to calculate and keep only +2 order moments. So we have developed method that we call POM, prediction of moments method, and it has following algorithm. All data is stored in moments m in the standard gauge. For each mesh point at each time step, we predict future values of moments using expression from previous slide. And from future moments, we calculate gauge and temperature and velocity pair. Using this gauge, we calculate the point from which we stream. Then at this point, we interpolate moments m. Then we, with the help of moments m, we calculate moments in moving frame d. From d, we calculate discrete distribution functions using Hermit expansion and stream it into the point x. After streaming in this point all needed distribution functions, we can calculate collision and new values of moments in standard frame m. So no iterations now. In this algorithm, each conservation law have its quadrature requirements. To provide mass conservation, we need to properly calculate second order moments because they are needed for prediction, which was on 2 slides ago. So to properly calculate second order moments, we need to use them in Hermit expansion when we calculate discrete distribution function, provide moment matching. So discrete distribution function becomes second order velocity polynomial. And when we, in the end of algorithm calculate second order raw moment, we must use quadrature that calculates integral for fourth order polynomial. Similarly, for moment and energy conservation, we can do the same. So to provide mass conservation, we have to use D3Q13 at least, and for energy conservation, D3Q45 at least. POM method was implemented as a program for GPU and tested on traveling vortex test. At step 1984, vortex has returned to its initial state, and as you can see, total mass, momentum, and energy are the same as at initial state. And on pictures, black circles are either density lines. Density values are listed higher. As you can see, the vortex shape is not distorted, and the main conclusion of this work that we developed the POM method as a conservative reg-pond method. POM saves mass, momentum, and energy when the parameters of quadrature, interpolation order, and regularization order fit the conditions. POM is more efficient than particles on demand since it uses minimal velocity quadrature and minimal interpolation stencils. And POM is more efficient than reg-pond since there are no iterations in POM and the scheme is explicit. We made a code for testing POM schemes, and POM demonstrates adequate results for a moving vortex and exact conservation of mass, momentum, and energy. Also, we have shown how we can construct such methods. Thank you for your attention.
Thank you too for the presentation. Let me see if we have questions from the audience. Probably not. Okay, I have a curiosity. In principle, you have in plan also to extend this approach to further higher momenta, like for instance the fourth momentum.
Yes, of course.
Okay.
Just we will have different requirements for quadrature.
Yes, okay.
And so,
Probably
and for
the
Hermit expansion.
Yes. Okay. Okay. Thank you. Okay. Thank you again. I can just clap also if I am alone, but this is the problem to be still in this pandemic situation. We can meet only by Zoom, but it's okay. So thank you again. Now on the schedule, we have a coffee break. So we will see you later at the 11 and 20 minutes. So we have 20 minutes of coffee break. So have a nice coffee. See you later. Thank you very much. Okay, we can restart. Welcome back to the session, the technical session 10, advanced method. Let me introduce the next speaker. She's Anastasia Perepelkina of the Keldysh Institute of Applied Mathematics in Moscow of the Russian Academy of Science. And the title of her talk is Fast Implementation of Moment Space Conversion in Lattice-Boltzmann Method Codes. Please.
Thank you for introduction. Can you hear me all right?
Yes, yes.
Okay, thank you. Well, the topic of this talk is maybe quite a small contribution. However, it greatly improved quality of life in programming complex lattice-Boltzmann codes. So I would like to share it with the community who actively use moment space transformation in lattice-Boltzmann codes. Let me remind of some moment definitions. We have raw moments, which are expressed through monomials. We can transfer to central moments where the velocity is taken from this point in space. And also Hermit moments are greatly used in many codes for gradient expansion, for Hermit moment expansion, for regularization in lattice-Boltzmann collisions, for validation of the method in Chapman-Cox expansion, etc. They're also used in the collision operators. The Hermit moments can be also used in a central form and also in a form of arbitrarily shifted velocity, where velocity is taken not from the current point, but from some point defined by the scheme, and also scaled with a temperature which amounts to a variable change in integration, where the variable is actually the argument of the exponent in the Maxwell distribution. The possible application that we found in the literature is a relative central moment collision, which stabilizes the collisions in the central Hermit moment spaces. And also our work, which is the generalization of the particles on demand scheme, where in particles on demand, there is a transform to the gauge that corresponds to the shifted velocity and scaled temperature. And we have extended the method by using the regularization expansion in this method by combining the particle distribution functions with shifted Hermit moments. So we also need to know the transformation from raw moments to shifted Hermit moments. So we find this method. I would like to know that it's becoming more and more complex when we have many dimensions and many degrees of freedom. So when the number of moments that we need to convert is quite huge. So I remind you the definitions of multivariate Hermit polynomials to introduce our notations. And here is an example of a transformation formula that we have found in this article. And for the first time in implementation, we have used this formula. However, as we see, when rising the order of the polynomial, is expressions become more and more complex, more indexes, more variants of different index combinations. And we here are the moments up to second order, and we use the moments up to 8th and 10th order. So the coding would be quite complex, and there is an expression through several sums and factorials, which is also quite complex. So we try to find a more simple and understandable and clear method of moment conversion. We base it on a recurrent expression for Hermit polynomials. The first line here illustrates how one index can be increased, incremented by one, and expressed through the Hermit polynomials of lower order. We take this expression and integrate it with particle distribution functions to obtain moments in a shifted with a shifted variable. Then we introduced a new notation. If the Hermit polynomial is expressed as a linear sum of monomials with coefficients lambda, then the new introduced notation with I, j, k at the top, the superscript, is defined as this kind of sum with increased orders in the monomial. Then the recurrent expression can be expressed in the new definitions as this line shows. After integration, we get shifted moments, for which we also introduced a new notation with ijk at the top. And the recurrent expression for the new moments is this formula with just 3 components. So this is how we convert raw moments to shifted Hermit moments. First, by definition, the raw moment of order 0 is equal to this new introduced D with superscript notation. Then the 4 expressions to increase in one order are like these 3. And by applying this formula several times, we transform to the shifted Hermit moments. So one complication that we found here is that we introduced a new notation in IJK. So it makes for 3-dimensional simulations this array of moments 6-dimensional. This is quite complex to implement. So we found another method. We were just looking at these expressions and found the dependencies with the increment in the lower and in the upper indexes. And what we found here is that what we see is actually a stencil scheme in the dimensions of alpha, beta, and gamma. So just look at these expressions. We see that there is local dependencies between neighbors in the alpha, beta, and gamma space. And we can illustrate it with a dependency graph for any number of orders and any number of dimensions as well. So And as in a stencil scheme, we have initial conditions and an output. And with the order of traversal of the dependency graph that is defined by these dependencies, we can find the correct order which transforms the set of moments to the set of shifted Hermit moments in place. So we do not need extra data to make or data copy to make this transform. So looking at this stencil scheme, we have implemented it as a code generation for C++. The code generation is written in Python with the comments for readable for the programmer. And here is the example for 3 dimensions for transformation up to order 3. The set of moments is shown here, and the example of code generation is written here. It implements a function which can take as arguments an array of moments, temperature and velocity, and shifts these moments to another moments. What we found here has greatly helped us in code implementations, because it not only makes the transform from raw moments to Hermit shifted moments, but also from raw moments to central moments, from raw moments to common Hermit moments, from equilibrium raw moments to equilibrium Hermit moments. So we just found this simple solution, and we just use this everywhere in our codes. So we would like to share it with the community as well. So as a conclusion, we introduced a method of moment space conversion that works for the conversion between multivariate raw moments, central moments, Hermit moments, central temperature scaled Hermit moments. With the use of this strategy, the coding of 6, 8, or any high number of high order moment conversions is clear and efficient in any number of dimensions. It is actually optimized for contemporary CPU and GPU, because this conversion can be localized in GPU registers and in L1 cache or in CPU memory. The conversion is in place, so we do not need the data copy. And the expressions are written so that optimizing compilers can understand it as a fused multiply-add operations. The procedure is implemented as a code generator in Python, so it can output the coefficients in any programming language that will be used in the later codes. Thank you. That's all.
Thank you for the presentation. Let me see if there are questions from the audience. Raise your hand if you want to present a question. Okay, I have a curiosity. How is the computational gain of use this approach in transforming the momenta instead of the classical ones, the classical approach?
Well, it depends on what you call a classical approach. I can compare it with a formula that is usually written in the appendixes of any paper. It's
exactly.
Usually a sum with several nested sums with factorials, etc. Well, the first thing is it is easier to code, like to
implement,
to write it without typos, etc. So it's easier in this way, and also it is easier to understand by the compilers, and the transformation is in place. To implement the nested sum, you need to at least to have a data copy to retain the moments that are still not converted. So
okay, so it is possible to avoid also the data copy. So
yes.
Yes, okay. Thank you. Thank you again for the presentation. And we can move to the next speaker, which is Noah Seekins from the North Dakota State University. I already gave you the permission to share the screen. Let me see.
Yep. Hello, can you hear me?
Yes, yes, yes.
Oh,
Absolutely.
perfect. Let me just finish getting things set up over here, and then I will go ahead and display the camera and share screen. Here's that.
Hi.
And then I have the screen button. There we go.
Okay.
All right.
Perfect.
Perfect.
Okay. So the title of the presentation is Faster Integer Lattice Gases. And the speaker is Noah Seekins. Please.
Good morning or good afternoon or wherever you are. My name is Noah Seekins. I am a graduate student studying with Dr. Alexander Wagner. And over the last sort of year or so, we've been working on creating a method to increase the efficiency of the integer lattice gas systems that were discussed a few times in several papers back in 2016. And there's mentions in a book in 1997. But yeah, so we've been doing work to increase the efficiency of those lattice gases. Oops, that is my alarm for the speaker. Apologies. I have forgotten to turn them off, so I will turn them back on, or turn them off. Anyway, so that is what we've been up to. This talk will cover just a little bit of lattice gas history, since it's not a super common topic, even in the fluid dynamic simulation circles, just so you can get a good idea of what the context is. And then we'll be discussing our algorithm, which is the Monte Carlo lattice gas in the diffusive case. And we'll discuss how exactly we developed it and how exactly we tested it. We'll show the timing results for the diffusive case, and we will discuss some of the challenges that we've encountered in extending this Monte Carlo lattice gas to the hydrodynamic regime, which we have a decent bit of progress on as well. So the first thing you got to know about lattice gases is sort of the history behind them. The first thing that comes up when you think about those is the Boolean lattice gas. In this case, we have the lattice gas equation, which is just your standard evolution equation, except for all of the values are discrete. So this is not a continuous equation like the lattice-Boltzmann equation. All of the numbers in this particular version of the lattice gas equation are Boolean occupation numbers. So either there's a particle at that particular velocity or there isn't. Now this was popular in the 1980s and 90s, but it had a couple flaws, which were, the big ones were that the lookup methods had difficulty scaling upwards to 3 dimensions, and the equilibrium distribution is not the same as the Boltzmann distribution, or the lattice-Boltzmann's equilibrium distribution that we would expect. It actually leads to velocity dependence of viscosity and other artifacts that aren't physical. Another sort of pitfall in the way of the lattice gas is that the company that was working almost exclusively on the lattice gases at the beginning there had a lot of progress and great results, but their research was proprietary. So the people in the field didn't have access to it, and eventually lattice-Boltzmann came along and sort of replaced everything, just due to the amount of work that was getting done on the lattice-Boltzmann compared to the lattice gas. So in about, there have been several different variations of the integer lattice gas over the years. Some people refer to it as multi-particle dynamics. Some people refer to it as the integer lattice gas. As the people in my research group, I'll refer to it as the integer lattice gas. I will be referring to it as such. In this version, the Ni become discrete integers, and this leads the equilibrium distribution to be the same as the lattice-Boltzmann, or at least the entropic lattice-Boltzmann. And this fixes almost all of the issues that the Boolean lattice gas has. It's fairly simple to scale up. The equilibrium distribution is okay, and the research is out there. However, it's not very efficient. The way that you have to end up doing this is by utilizing random collisions and selecting a random particle C amount of times given the number of collisions at each time step does not necessarily make for an efficient system. Thus, our idea is to try and improve the scaling of this collision operator. And the idea, which was originally suggested by Bruce Boghossian, is that since the effect of the collision operator is to bring the NIs closer to equilibrium, we can define a new NI for each collision by sampling from the equilibrium distribution locally. Now, the big reason that this is not something that's common to do is that the equilibrium distribution for these samples are of V minus C dimensions, right? So in the D1Q3 case, it's not super bad, right? You get a two-dimensional surface inside a three-dimensional space. However, easily you can see how if you're going up to the D2Q9 or even the D3Q27 systems, that this becomes much more complicated as you have an 8 or a 26 degree dimensional surface inside of a 9 or a 27 dimensional space. And those aren't easy to sample from. However, we found that in essence, you can decouple the axes. So instead of doing for the D1Q3 case, one sampling in a three-dimensional or in a two-dimensional system in a three-dimensional space, you can only do, or you can do two samplings each in a one-dimensional surface. So in this case, we would sample a point along the N0 axis and then a point along the N1 axis. And since there's only three axes and our particles are conserved, that would define the point of the N2 axis on which we would have to be. So the simplest case for this, and the one that we've set up as our test case, is the diffusive lattice gas. Thus, the first thing that we do is impose a local equilibrium distribution where we get our Fi equilibrium is equal to our Boltzmann distribution of Ni, given a maximum number of N particles at the lattice site, which we define as NWI, where Wi is the weight for each velocity, and the sum of the weights has to be 1. So we impose this local equilibrium distribution by demanding detailed balance in which the equilibrium state of I has times the probability of having a particle move from velocity I to velocity J has to be equal to the equilibrium state of J times the probability of a particle moving from velocity J to velocity I. And of course, in a simple-ish manner, we can demand this detailed balance by setting your probability of moving a particle from I to J as the weight of I. There is something to note here. There is other work that has first taken the lattice-Boltzmann collision step and then estimated the sampling from there. We demand detailed balance first, which instead of imposing the local equilibrium distribution. And this is not super relevant in the diffusive case, but when we get to the hydrodynamic case, we have Fi equilibrium of rho and u can be imposed versus having the Boltzmann time step. So this diffusive case, this doesn't super change anything, but in the hydrodynamic case, it changes a lot more. So for our diffusive system, for our diffusive system, we look at the local equilibrium distribution. We have found that the local equilibrium distribution ends up being a multinomial distribution, which is defined as such. For our diffusive lattice gas, we can sample from the multinomial distribution by sampling from successive binomial distributions. So as long as you're taking the particles out of your total number of particles, you can sample from the successive binomial distributions. We have found that using the new scientific library, or the GSL, is efficient in this case to sample from a binomial distribution. We've also created our own method of sampling. However, that is not something we're going over in this presentation. It is important as well to talk about how we've undertaken partial collisions. So in order to undertake partial collisions, we define the fraction of collided particles in a given time step as omega. And thus we use omega as a probability for collision and sample the particles to be collided in each velocity utilizing a binomial distribution. Thus, we take the probability of n particles being collided in a velocity with a total of n particles becomes P of n equals capital N over n, omega to the nth power 1 minus omega to the n minus n power, which is just your standard binomial distribution. This is specifically for under relaxation. We do not have over relaxation yet implemented in this system. But this allows us to look at the hydrodynamic limit. We take the ensemble average to get the Boltzmann equation with Fi of x plus Vi t plus 1 equals Fi of x and t plus our psi I, which is omega times rho of x and t Wi minus F of I of x and t, where we get rho is the sum of our Fi's. We also demand that our Vi Wi are 0 and Vi squared Wi equals d theta. And when we Taylor expand this, we end up with the standard diffusion equation, or differential with respect to t of rho of xt equals differential with respect to x of 1 over omega minus 1/2 theta dx rho. So before we talk a little bit more about the solutions to the diffusion equation that we end up with and that we're using to test, we decided to test the total equilibrium distribution that this comes to. As you can see, these are all Poisson distributed equilibrium distributions, and this is with a density of around 5 average particles per lattice site, which the lattice Boltzmann would fail to do for this low of a density. You can see on the left here, here's our graph with all of the different velocities. We have some of the velocities grouped together because those velocities have equivalent weights, and thus their Poisson distributions are equivalent in shape. And then over here on the right, you can see how we've labeled the axes. Okay, so in order to look at the evolution of the system, which is our next testing step, we decided to set up a sinusoidal profile utilizing Poisson distribution. This allows us to be the final, allows us to utilize the following solution to the diffusion equation to compare our results to our theory. So this would be our theoretical distribution that we end up with, which is an average of times 1 plus sine 2 pi x over Lx times the exponential of negative 4 pi squared dt over L squared x, where d is just derived from our hydrodynamic limit with d equals 1 over omega minus 1/2 times theta. And you can take a look at how that turns out here. You can see on the left here, this is specifically looking at the amplitude of the system. So as you can see here, the amplitude is decreasing over time. And these amplitudes follow the straight lines as the theory and the jagged or bolded lines as the measured values. You can see they sort of go towards randomness at the bottom. That's just because the fluctuations start to take over as your system goes more and more towards equilibrium. And this is just showing the decay of the sine wave is well recovered for different relaxation times or diffusivities. The next important thing to look at was the efficiency, as one of the main things that we were looking at was how to make the integer lattice gas more efficient. And with the Monte Carlo lattice gas, we do end up seeing that there is a more efficient system there. The red lines here are the lattice Boltzmann methods. The pink lines with the blue squares are the integer lattice gases. So the blue squares are the measured values. The pink lines are the approximate representations of those measured values in the long term. These are all in million lattice updates per second. For some reason, that graph title didn't update. I'm sorry. But here then we have our Monte Carlo lattice gas, which is utilizing the GSL, which you can see, though it is not quite as efficient as the lattice Boltzmann, it is definitely within an order of magnitude or so, which is much better than the integer lattice gases in the past. Along with this, we are not entirely sure whether this is completely optimized. We are almost certain that there is more to be done, as we are not computational efficiency experts. So it's entirely possible that this could be as fast or faster than the lattice Boltzmann in the future. The next big challenge that we had was converting this to a hydrodynamic system, which this is a little bit about our next project. So we'll talk about this here. So due to the requirement of momentum conservation, we need binary collisions. We set up a detailed balance, which applies to the binary collisions similarly to how our detailed balance applied to the single collisions. We just go from ij to kl and kl to ij, as opposed to I to j and j to I. The resulting equilibrium distribution isn't as simple to sample as the multinomial distribution would be. So we have to find what that distribution actually ends up being. So in the D1Q3 system, which is the main body of progress that we have so far, we have determined that instead of sampling directly from the particles and the velocity distribution, as we did in the diffusive case, we've decided to sample from the moments, most specifically the energy moment, which is this pi moment right here, as n and j are both locally constant, as this represents the total number of particles and this is the momentum. So these have to be globally constant and locally constant through a collision. So this pi moment is what we're going to be sampling. As you can see here, given that n and j are constant, as long as we know pi, we can determine the values of all of the velocities. And we can utilize this to find an equilibrium distribution. So we take our detailed balance, where we have our transition probability of pi to pi plus 2 versus pi plus 2 to pi. Since we're doing binary collisions, the only operations that are allowed are to have two particles move from moving to rest particles, or have two rest particles become moving particles. That's the only way that momentum can be conserved. Thus, if we utilize these transition probabilities, the chance of picking a rest particle or two rest particles and multiplied by your weights, and the probability of picking two moving particles that are moving in opposite directions, along with your weights, we end up with this recursive relation for the probability distribution P of pi. We don't exactly know what this is. It's not a binomial distribution, but we haven't quite figured out an explicit formula. However, the recursive formula is good enough for implementation in the first case. So the other big thing is that we've determined, utilizing a similar algorithm utilized by Blommel et al., who have created a working hydrodynamic lattice gas, which utilizes two particle random collisions in order to simulate. When we take the equilibrium distribution for a two-dimensional system of both x and y, it agrees with our theoretical distribution that we've determined here. And a system will fall into equilibrium in the same way for both x and y. So since this isn't simple, we don't quite know what we're going to do for sampling, as a library like the GSL may not exist, but we're still looking into implementing. That leads us to our remaining steps to implementation. We figured out how to implement a 1D simulation fully, and are working on that as we speak. And two-dimensional sampling is also something we've speculated on, but haven't entirely confirmed as of yet. Since the equilibrium distribution is confirmed, however, we are fully implementing it in the 1D case, and we'll work on scaling the system up following successful implementation. All right.
Okay.
Are there
Thank
any
you.
questions?
Thank you very much for your presentation. Let me see if there are questions from the audience. It seems not. At the same time, I can just ask you. I am curious about the fact if your simulation are still in serial code or in parallel. Have you?
These are still implemented in serial. We
Okay.
have theories for how we might implement them in parallel, but in that case, we would have to compare it to a parallel fluctuating lattice Boltzmann simulation, which we don't have access to as of right now. We've got ideas of how we might parallelize this code, but we haven't implemented them as of yet.
But you think that this can change the results in terms of computational efficiency when you compare your model, your method with the other ones?
Potentially.
Potentially.
Like, I'm not super familiar with how parallelization scales this particular code and how it scales the lattice Boltzmann. So I'm maybe not the best person to talk on that.
Okay. Then, yes, thank you. So thank you again for the presentation. So now we are moving on to the last but not least speaker of this session. He is Professor Mohammed Hossein Sadat from the ETH of Zurich. Sorry for my pronunciation.
No, that
correct me.
I'm just not a professor. That was
Doctor, okay.
Not even doctor. I'm a PhD student.
Okay, PhD student.
Actually, yeah, but
Okay, so this is like how you say, a wish for the future. So
yeah, thanks.
okay. So the title of your presentation is Extended Lattice Boltzmann for Compressible Turbulence. Please go ahead. I think no, I have to give you the permission. Okay, now you can share your screen.
So, can you see my screen?
See, yes, please.
Okay, so thank you very much. My name is Hussein. I am a PhD student in the group of Professor Carlin. And as you said, what I'm going to talk about today is about a lattice Boltzmann model for the simulation of compressible turbulent flows. So, as you know, lattice Boltzmann actually has been very successful for the simulation of incompressible flows. But when it comes to the compressible flows, it faces severe numerical challenges. And these challenges even become more prominent if we have supersonic flows where there are discontinuities in the flow field in the form of shock waves. So then the question that arises is where this problem is coming from and what is the source of this limitation and all these challenges. So in order to answer that question, what we can do is that we can have a look at the simple lattice Boltzmann equation with the BGK collision term on a standard lattices. And by standard lattices, I mean, for example, D2Q9 lattice in 2D or D3Q27 lattice model in 3 dimensions. If we find out the hydrodynamic equations using the Chapman-Enskog analysis, what we will see is that we can recover the continuity equation correctly in the hydrodynamic limit, but but in the momentum equation, there will be an additional term, this X here, this additional spurious term in the momentum equation, which actually has a form like this. So it is actually proportional to this Q hat, and Q hat is the deviation that we have in the third order equilibrium moment compared to the Maxwell-Boltzmann moment. The reason that we have such a limit, such a deviation, is that the number of discrete velocities of the standard lattices is too low. That means that we always have this closure relation like this, meaning that the diagonal components of the third order equilibrium moment is always equal to the first order moment. So that means that regardless of the equilibrium distribution function that we use, we always have this deviation in the third order moment. Now, if we are in the isothermal incompressible regime, we can set the temperature to be fixed at 1/3. That removes this linear term from the deviation, and we are left only with the cubic term. And this cubic term is negligible when the flow velocity is small. But as soon as the flow velocity becomes large or there are temperature dynamics in the system, then we have to take care of this deviation in some way. And there are actually different ideas for doing that. So the first idea that comes to mind is to, so if the problem is coming from a small number of discrete velocities, then we can just increase the number of velocities and use the so-called higher order lattices or multi-split lattices with more discrete velocities. This idea actually works well, and it guarantees the Galilean invariance of the model. But the price that we have to pay is that the computational cost increases, and also the temperature range of these higher order lattices is somewhat limited. Now, the next idea that we are using in this study is to use correction terms. So in this approach, we are still using the standard lattices, so we can take advantage of its simplicity and efficiency. But then we add some correction terms into the equations in order to remove the spurious terms in the momentum equation I mentioned in the previous slide. Now this implementation actually, I mean, there are several proposals in the literature for that. And the one we have used here is based on the idea that we can simply extend the definition of equilibrium distribution function by redefining the pressure tensor. So we know that we can write the equilibrium distribution function as a product form like this, where U is the flow velocity and P is the pressure tensor. Now, if we define the pressure tensor to be equilibrium pressure tensor plus this additional term, which contains this deviation in the third order moment, then those spurious terms will be removed. And this could be shown through Chapman-Enskog expansion. So now that we took care of the momentum equation, the next question is what to do with the energy equation. And for this, there are also multiple proposals in the literature. The first one is to stick with the one population setting and add even more correction terms in order to get the correct energy equation in the hydrodynamic limit. This approach actually was first introduced in 2008, and it works well. But the problem is that it has rather complex correction terms. The second approach is called the hybrid approach. And the idea is that we can solve the total energy or the entropy equation using conventional numerical schemes like finite difference or finite volume. And finally, the approach that we have used in this study is the two population approach, where we have an additional set of populations responsible for conserving the total energy. Now, with that being said, we can have a look at the compressible model that we propose. So as I said, we are using the two population model. So we have two populations. The first one, F, is for the conservation of density and momentum. The second population, G, is for the conservation of total energy. In the F equation, we are using the extended equilibrium, as I said, to take into account the deviation in the third order moment. And for the G population, the equilibrium population is actually computed using the moment matching. That means that we are recovering all the Maxwell-Boltzmann moments of the energy distribution function. And finally, we need also a quasi-equilibrium population to have control over the Prandtl number. And with Chapman-Enskog expansion, we can show that this quasi-equilibrium population needs to be different from equilibrium population just first order moment. So the first order moment of G star should be equilibrium moment plus this additional term here. And this additional term ensures that we are recovering the correct viscous heat dissipation in the hydrodynamic limit. So now with this model, this is the first test case that we consider the Sudshock tube. So here you can see the results of density profile and velocity profile compared with the exact solution. And so you can see the agreement is very well apart from minor oscillations here close to the discontinuity. The next validation case is the shock vortex interaction that is passing a vortex through a shock wave. So in this problem, we have a standing shock wave with Mach number of 1.2. And then there is also an isentropic vortex with vortex Mach number of 0.25. So this vortex is initially upstream of the shock wave, and then it goes through the shock. And here on the right, you can see the comparison of radial sound pressure distribution with the DNS results at 3 different times. And again, the agreement also here is very good. So now after validating the model, we can now turn to a more complex case of compressible decaying turbulence. So the problem here is that, so we have a box with size L, and then we initialize the flow field inside the box with constant density, constant temperature, and then the initial flow velocity follows a specific energy spectrum. Now the parameters for this problem, first is the turbulent Mach number, which is defined like this, and also the Reynolds number based on the Taylor microscale like this. So here the URMS is the root mean square of velocity as lambda, and lambda is the Taylor microscale, which is defined like this. So in the first scenario, we consider the turbulent Mach number to be 0.3 and the Reynolds number to be 72. Here you can see the time evolution of turbulent kinetic energy on the left and turbulent Mach number on the right. We have also done a grid study. We have used 3 different grid sizes, and you can see that the grid size with 256 grid points in each direction can actually capture the evolution of kinetic energy and turbulent Mach number very well. Then in this slide, I have compared other statistics. So the left picture shows the root mean square of dilatation, and the right picture shows the root mean square of density. And here again, the 256 grid points is actually enough to accurately capture, especially the dilatation, this rapid increase, this initial rapid increase in the dilatation, and then its decay afterwards. Also, the result of root mean square of densities is, in comparing with DNS, is also quite satisfactory. Now we make the situation a bit more complicated by increasing the turbulent Mach number to 0.5 with the same Reynolds number. And what happens actually in this case is that random shock waves known as eddy shocklets appear in the flow field. So the left picture shows the isosurface of velocity divergence colored by local Mach number. And you can see the supersonic regions in this picture in red color. And also the root mean square of density is compared in the right picture using 2 grid points. And again, even for this high Mach number, the 256 grid point is enough to capture the DNS. And finally, we also increase the Reynolds number here in this case. So the Mach number, the turbulent Mach number is still around 0.5 or 0.488 to be precise. But the Reynolds number is now increased to 175. And here I have shown again the time history of turbulent kinetic energy, of Reynolds number, Taylor microscale Reynolds number, and also the dissipation rate, which is a sensitive parameter, and they are all agreeing well with the DNS results. So in conclusion, what we did here is that we proposed a compressible lattice Boltzmann model in 2 population framework, and with the help of extended equilibrium, we showed that the model can simulate compressible turbulent flows, and it can capture the compressibility effects, turbulence fluctuations, and also shocks. Now, what we are working on right now is to first extend the model to high Mach number applications. Then we can also enhance the stability of under-resolved simulations of this model by using probably more advanced collision terms like multi-relaxation time and so on. And finally, we have to test the model for compressible turbulence involving wall boundary conditions. So with that, I would like to finish my presentation. Thank you very much for the attention. And
thank you. Thank you very much. We have already a question from Christoph. Question 1. It is surprising to see that you are talking about errors in third-order moments for standard lattice, while your colleagues were pretending that there is no issue earlier this week. I think this is not related to your work directly.
Okay,
exactly. You cannot answer. How does your method compare to compressible D3Q19 hybrid lattice Boltzmann that have been used in the industry for almost a decade in terms of accuracy, efficiency, and robustness?
Yes. So regarding the first question, yes, of course, I have this deviation in the third order moment, but in Pond, there is no such a deviation when you are in the co-moving reference frame. So I am in the 0 reference frame, Pond is in co-moving reference frame, and in co-moving reference frame, there is no error in the third order moment. And the second question, yes, I actually have not compared quantitatively our model with the hybrid models. So I cannot make any statement about the accuracy or efficiency of our model compared to hybrid models. And yeah.
There is another question from Gauthier. Do you use a shock sensor for the test cases, or do you use a constant viscosity?
Yeah, no, there is no shock sensor in this model. We are using constant viscosity, and the value of the viscosity, actually, I don't remember at the moment, but it is constant. There is no shock sensor in the model.
You have a curiosity? This is mine. You have in plan also to use entropic correction to increase the Reynolds number.
Yeah, of course, yes. So entropic collision term is one way to increase the stability of the model, yes.
Okay, okay. So thank you again for the presentation. This is the last presentation of this technical session. So I want to remind that now there is the lunch break. We will restart at 2:40 p.m. with the plenary talk given by the speaker Adriano Tiripocchi. And for this afternoon, we will have only a session in the room Leone. That will be the technical session 12, and the topic will be the boundary conditions. So thanks again to all the speakers, and thank you to all the audience for the kind attention. So have a nice lunch, and we will see later in the afternoon at 2:40 p.m. Thank you again. See you later.